Hey there, science fans! Today we're diving into the fascinating world of atoms and their tiny inhabitants, electrons. Specifically, we're going to unravel the mystery of electron configuration, the way these minuscule particles arrange themselves within the atom. Imagine atoms as bustling cities and electrons as their residents. Just like people choose different neighborhoods and houses, electrons occupy specific regions within the atom. Understanding electron configuration is like having a map to this atomic city, revealing the location and behavior of those tiny residents. So, buckle up as we embark on this subatomic adventure. We'll explore the rules governing electron arrangement and learn how to decipher their configurations. By understanding these patterns, we can predict how atoms will interact with each other, form bonds, and create the incredible diversity of molecules that make up our universe. Before we dive into the specifics of electron configuration, let's take a moment to review the basic structure of an atom. Atoms are the fundamental building blocks of matter, so small that millions of them could fit across the width of a human hair. At the heart of every atom lies the nucleus, a dense, positively charged core. The nucleus is home to two types of particles, protons and neutrons. Protons carry a positive electric charge, while neutrons are electrically neutral. Together, protons and neutrons account for almost all of an atom's mass. Whizzing around the nucleus like planets orbiting a star are the electrons. Electrons are much lighter than protons and neutrons and carry a negative electric charge. The number of protons in an atom determines its atomic number, which defines the element to which it belongs. It's the arrangement of these electrons, their specific locations and energy levels, that we refer to as electron configuration. Electrons, those tiny particles zipping around the atom's nucleus, aren't just randomly scattered. Think of it like this. Imagine the nucleus as a stage and the electrons as performers. Just like performers on a stage occupy different levels, some on the main floor, others on balconies. Electrons occupy different energy levels within the atom. These energy levels, also called electron shells, are like concentric circles surrounding the nucleus, each representing a specific energy state. The lowest energy level, closest to the nucleus, is like the best seat in the house. It's the most stable, and the one electrons prefer to occupy first. As we move further away from the nucleus, the energy levels increase, like moving to higher balconies in our theater analogy. Each electron shell has a limited capacity, meaning it can only hold a certain number of electrons. The first shell, closest to the nucleus, can hold a maximum of 2 electrons. The second shell can hold up to 8, and the third can hold up to 18. This arrangement of electrons in different energy levels is a key factor in determining an atom's stability and its ability to interact with other atoms. We've learned that electrons occupy different energy levels within an atom, like performers on different levels of a theater. But within each energy level, there are also specific sublevels, or orbitals, where electrons reside. Think of these orbitals as individual seats within each balcony. But electrons aren't just randomly filling these seats. Their arrangement follows a set of rules, like a cosmic seating chart, that governs their distribution within the atom. Let's explore these rules, which are crucial for understanding electron configuration. The Aufbau principle. This principle states that electrons first fill the lowest energy levels available. Hund's rule. This rule states that when electrons occupy orbitals of equal energy, they prefer to occupy them singly before pairing up. The Pauli exclusion principle. This principle states that no two electrons in an atom can have the same set of quantum numbers. These rules, working in concert, dictate the specific arrangement of electrons within an atom, determining its chemical properties and how it interacts with other atoms. By understanding these principles, we can predict and explain the behavior of elements in chemical reactions. This knowledge is essential for advancing scientific research and technology. Section 5. Electron configuration notation, a shorthand. Now that we understand the rules governing electron arrangement, let's learn how to write electron configurations, a shorthand notation that tells us the distribution of electrons within an atom. It's like having a seating chart for each element, revealing which orbitals are occupied by its electrons. Electron configuration notation uses a combination of numbers and letters to represent the energy levels, sublevels, and number of electrons in each. Here's a breakdown. This number indicates the main energy level, like the balcony level in our theater analogy. Each energy level is divided into sublevels represented by letters S, P, D, or F. A superscript next to the sublevel letter indicates the number of electrons occupying that sublevel. For example, 2p circumflex 4 means there are 4 electrons in the p sublevel of the second energy level. Let's look at a simple example. The element lithium, which has an atomic number of 3. Its electron configuration is 1s squared 2s circumflex 1. By using this shorthand notation, we can represent the electron arrangement of any element, providing a powerful tool for understanding their chemical behavior. Section 6, Electron Configuration and the Periodic Table. The periodic table, that iconic chart of elements, is not just a random arrangement, it's a masterpiece of organization, with elements grouped based on their properties and atomic structure. And guess what plays a key role in this arrangement? You got it, electron configuration. The periodic table is arranged into rows, called periods, and columns, called groups. Elements in the same group share similar chemical properties because they have the same number of valence electrons. Electrons in the outermost energy level. These valence electrons are the social butterflies of the atom, responsible for forming bonds and participating in chemical reactions. As we move across a period, the atomic number increases, and so does the number of electrons. This means that the electron configuration changes systematically, with electrons filling orbitals in a predictable pattern. This pattern is reflected in the periodic repetition of chemical properties, which is why the table is called periodic. For example, all the elements in group 1, the alkali metals, have one valence electron in an s orbital. Understanding the relationship between electron configuration and the periodic table is like having a cheat sheet for chemistry. Now let's take a closer look at electron configuration itself. Each electron in an atom is assigned to a specific orbital, which is defined by a set of quantum numbers. These numbers include the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. Together they describe the energy, shape, orientation, and spin of an electron within an atom. The arrangement of electrons in these orbitals follows a specific order, known as the Aufbau principle. According to this principle, electrons fill the lowest energy orbitals first before moving to higher energy levels. This is why we often see configurations written in a specific sequence, like 1s2, 2s2, 2p6, and so on. The Pauli exclusion principle further refines this arrangement by stating that no 2 electrons in an atom can have the same set of quantum numbers. This means that each orbital can hold a maximum of 2 electrons, each with opposite spins. Understanding these principles helps us predict the electron configuration of any element and gives us insight into its chemical behavior. So, what are the real-world applications of understanding electron configuration? Well, it's pretty fascinating. For starters, electron configuration is crucial in the field of chemistry and material science. It helps scientists design new materials with specific properties like superconductors, semiconductors, and even new pharmaceuticals. In the world of technology, the principles of electron configuration are applied in the development of electronic devices. For example, the behavior of electrons in different materials determines the conductivity and efficiency of components like transistors and diodes. This knowledge is essential for creating faster, more efficient electronic devices. Moreover, electron configuration plays a vital role in understanding and predicting chemical reactions. By knowing how electrons are arranged in an atom, chemists can predict how an element will react with others, what kind of bonds it will form, and even the color of compounds it might create. So as you can see, the principles of electron configuration are not just abstract concepts. They have practical applications that impact our daily lives in numerous ways. Finally, let's talk about the importance of electron configuration. Understanding electron configuration is fundamental to the study of chemistry and physics. It provides a framework for understanding the structure and behavior of atoms, which are the building blocks of matter. Without this knowledge, we wouldn't be able to explain why certain elements behave the way they do, why they form specific compounds, or why they have particular physical and chemical properties. Moreover, electron configuration is essential for advancing scientific research and technology. It allows us to develop new materials, create innovative technologies, and find solutions to complex problems in fields ranging from energy to medicine. In essence, electron configuration is the cornerstone of modern science.